Nuclear magnetic resonance. So obviously, this technique is focused on the nucleus of the atom. And we can distinguish among the different atoms. Nuclear magnetic resonance can be used for any element that has an odd number of protons and or an odd number of neutrons. And we'll explain why that is in just a second. So it can be used. We're going to focus on hydrogen because it's only got protons, actually. It's only got one proton. So it's susceptible. I mean, it's active. Nuclear activity. It's active. And then we'll look at carbon. So there are our topics, and there are a lot of them. So let me move this up out of the way and decrease the size. There we go. I already said that. It gives us information as to both the number of hydrogen and carbon atoms with the technique that we're going to be describing. Not only the number, but the types. In other words, and this is based upon primarily their position, their connectivity in the molecule. Connectivity tells us, I mean, if we have a formula like C3 CH2O, we know, I've used this one before. This one could be, let's see. What I'm trying to do is ethanol. So there's carbon, oops, too many. 1, 2 carbons, 3 hydrogens here, 2 there. That needs to be there. This could be ethanol, or it could be ether. That wait a minute. Let's start over. It could be CH3 CH2. Could be this one, or it could be this one. They have the same formula. This one's methanol, and this one is dimethyl ether. Nuclear magnetic resonance will produce a spectrum that is unique for each one. You can tell the difference between them, whereas their molecular formula doesn't tell you that. So it gives you connectivity of each of the atoms in the molecule eventually. Right? It's another detective story, but it is extremely powerful. All right. Then what we want to do is, infrared spectroscopy is not useless, but it doesn't provide any information about connectivity. Infrared spectroscopy is essentially functional group information, like bond stretches and bends. And UV visible spectroscopy is even less in terms of connectivity. It's basically a quantitative procedure. Now, infrared spectroscopy, we know, is uses the infrared part of the spectrum. Like we have visible here, and we have gamma rays out here. Oops, that's alpha. Gamma rays out here at the high frequency short wavelength. Go through visible, and we get out here to radio waves, right? Radio. Then we know on this side, the longer wavelengths, this is infrared, and this is ultraviolet. There's visible. Well, past infrared is microwaves. And here we have ultraviolet and X-rays. Okay, so with infrared spectroscopy, we're in this region. We're irradiating our sample with this. Ultraviolet and visible, we're using this range. All right, I already said that. For nuclear magnetic resonance, we're using radio frequency. We're out here. So very long wavelength, small frequency. Low frequency, long wavelength. Now that seems counterintuitive because to me it does. Because we usually think of molecules where we have bends and stretches. It takes less energy to make that happen. And it takes a little more energy to get to move electrons and get the visible and UV. And then when you get down to the nucleus, the forces in the nucleus are massive compared to the electron movement. So you would think we need X-rays and gammas. Well, if you want to split the nucleus apart or really do some damage, that's what you want. But we want information. So we just want to use a part of the spectrum that will resonate with the nucleus in a certain way. So we use these radio waves. These photons have less energy, obviously, based upon what I've shown you there. And the frequencies are typically between 3 hertz. So it's a very, very broad range of frequencies, 3 hertz and 3 times 10 to the 11th hertz. So you have 10 orders of magnitude, 11 orders of magnitude, right, range. So this is a really broad spectrum, radio waves. Most modern nuclear magnetic resonance spectrometers, however, stay within between about 10 to the 7th and 10 to the 9th hertz. So this radio range is this, but 10 to the 7th to 10 to the 9th hertz is typically where we stay. And this is what a schematic of a nuclear magnetic resonance spectrometer. Your sample has to go down inside the spectrometer because it has to be in an extremely strong magnetic field in order for this to work. So it requires a superconducting magnet. And if you want, just think about if you've ever seen an magnetic resonance imaging device in a hospital or in a clinic, then you can think of this thing turned on its side, when the patient goes in the hole. They go into that strong magnetic field, and then they're irradiated with radio waves and produces a return signal at the same frequency as the one imposed on you. So the magnet has to be, in order to be that strong, it has to be superconducting. So it has to be cooled down. Some of them will use liquid nitrogen now. Some still use liquid helium. Very, very cold. Liquid helium is the coldest substance known. It goes down to 4K. in bulk amounts. So then we get a signal amplitude, which is roughly proportional to how many atoms are being irradiated at that particular position. Now, the position in an NMR spectrum, when you irradiate the signal that's in this magnetic field and it returns a signal, the graph is not reported in terms of frequency, because like we do with IR and UV vis, you don't have frequency on the x-axis. What you have is a manufactured value, because the frequency that's returned is the same one you irradiate with. So you have to look for other differences in the way it resonates. That we call the chemical shift. And the chemical shift, notice the arrow's pointing left, because the chemical shift starts at 0 on the right and gets bigger going to the left. I think that's a artifact from history of NMR. So there's your typical setup. The solution that you use is important, because it's going to be in that magnetic field and susceptible to the frequency as well. So typically one type of solution that you'll use is deuterated solvent, like trichloro-deuteromethane. The reason you use that is because the frequency, the resonant frequency for chlorine and deuterium are not being used in the instrument. So they're invisible. And the carbon is invisible too. You select your wavelength, your frequency, so that it will ignore those. And then you put the tube down in the hollow bore of the magnet, where it's irradiated with short pulses, just a few microseconds of radio frequency. And then the RF return signal. So you use the same emitter is also the receiver. So you have to do it in pulses. You emit, and then in a microsecond, you turn it into a receiver, and it goes back and forth like that. All right. Most devices will deliver a range of frequencies, so you can tune it to whatever element you're looking for, right? Typically hydrogen or carbon. That's nothing new. Some of these I put in here, and I'm going to skip them anyway. So we need this very high external magnetic field, which is designated as B external. B refers to magnetic field. So you're irradiating it. No, you're delivering an external magnetic field, B external. The reason you have to do that is because the nuclei are randomly oriented. The protons and neutrons are randomly oriented. So we think of them as spinning. They probably don't do that, but it's a simple way to explain what's going on. So you think of like this proton might be spinning like this and producing a magnetic field in that direction. But there are lots of other protons in there. And if they're even numbered, they're going to cancel each other out. If they're odd numbered, then the chances are you'll find one that is not balanced, and you can use that as your target. That's why the even numbers are not NMR active, and the odd numbers are. Okay, so you have this very strong external field. A small portion of the radio frequency, then you irradiate. Like once you get this strong magnetic field, you irradiate it with your radio frequency, and it emits at exactly the same frequency. That's why you have to turn it on and off, switch back and forth. So the logical question is, I mean, if it's emitting at the same frequency, what kind of information can you get out of it, right? Well, when you irradiate it with a certain intensity, it returns with a different intensity. So this is the return, and this is the applied. So it will absorb some of that radio frequency and give you a return signal that's different in intensity, not in frequency, but in intensity. So you record this re-emitted radio frequency radiation over a period of a few seconds. So it's not a fast scan. Right? That's probably why they keep you in the MRI for 15 minutes. If it were a fast scan like a CAT scan, you'd be in there for like 5 minutes total, and they get everything they need. But for NMR, you got to be in there for a while. If it's a small sample and you're only looking at one molecule, then it just takes a minute or two. But if you're a human-sized body, then you got to stay in there forever. Okay, so what are we looking for? Over this period of time, it produces what's called a free induction decay. So that has to do with the absorption of that light, and then it emits only a certain amount of it. So many free induction decays are acquired and are averaged. So we average all these induction decays in a mathematical algorithm called a Fourier transform. Fourier transform is it's a statistical way of treating signals that come from samples. I've seen it used in infrared spectroscopy. It's extremely useful. It got its start with sound waves. Sound waves would be superimposed on each other, and with a Fourier transform, you can separate them into a two-dimensional pattern and get information from them. But the mathematical transform was then ported over to other techniques. And this is one of them. So the Fourier transform then takes all those signals. The algorithm that is part of that transform decomposes this free induction decay into individual frequencies called signals. Now, I'm not sure if that's what the author calls them, individual frequencies, but I'm not sure that's correct. They're individual signals. Just put it that way. They could be manufactured frequencies that convert the information into frequencies that then can be separated. Then the amplitude of each signal is proportional to the amount of radiation that was originally absorbed. So if one hydrogen proton absorbs a certain amount, then two will absorb twice as much. And that will increase the amplitude of your peak. So the x-axis of the NMR spectrum is called the chemical shift, often abbreviated as small d or delta, Greek letter delta, chemical shift. All right, now let's see if we can explain why it happens. We place the sample in a strong magnetic field because, without being subjected to a strong field, a sample doesn't absorb RF radiation, and therefore we cannot produce an NMR spectrum. So it has to be in a strong field. Now, why does it have to be in a strong field? A nuclear spin generates a small magnetic field, and a proton can assume one of two spins. Just like electrons can have one of two spins. When we did our electronic configurations, get down to you have N, L, and then the M sub L, and the M sub S. S can have a +1/2 or a -1/2. That's for electrons. Same thing can happen for protons and neutrons. They can have spins. They can spin up or spin down, or spin left or spin right. It can assume one of two different spins, either an alpha spin or a beta spin, we say. Like tiny bar magnets. So on the left, with no magnetic field, they're just randomly distributed, alpha spins and beta spins. Right? So if you shine radiation on them, it may be absorbed by one, and well, they'll cancel each other out. When they absorb and re-emit, they just all, since they're random, they cancel out, and you can't get a spectrum, can't get an absorption out of them. But if you put them in a strong magnetic field, then the ones that are initially, the ones that are pointing this way will orient with the field, and the one pointing the other way will orient opposite the field. That's what in a magnetic field. And you get shifting back and forth between those, but it's not even. So if you have 1, 2, 3, 4, 5, 6, 7, 8, well, that's not a good choice because that's an even number. But be that as it may, the external field causes them to orient either alpha or beta. And alpha is considered the lower energy spin state, beta is considered the higher energy spin state in this external field. Let's see. I ought to take advantage of my animations. Okay, random directions first. Then when you put them in the field, each nucleus with a spin has its average magnetic dipole aligned parallel to the B external field. All right. Dipoles of the nuclei in the beta spin become aligned against it. Since they're higher energy, that's probably why there are fewer of them. Okay. The difference in energy between the two is known as the delta E spin. And is as the external magnetic, the strength of the magnet increases, so does the difference in energies between the alpha and the beta state. So the stronger the field, the further apart those energies are. Okay, so now we got one where we see energy here, and that's where it's not irradiated first. Right? You just have whatever the molecule is given for its nuclei at alpha states and beta states, then you irradiate it. And if you irradiate it, then some of the alphas are going to absorb that radio frequency and be promoted to the beta state. And then they will re-emit the signal when they relax, just like electrons when they fall back into a lower orbit, they'll emit. Nuclei do that also, only they do it based on spin. Okay. We call that a spin flip when they absorb energy. So when it relaxes, radio frequency is emitted at the same frequency which it was irradiated originally. And okay, the alpha and the beta spin states have exactly the same energy in the absence of an external field. When you apply the external field, then you get the energy difference. All right. So this signal is given off when we switch the emitter back to the detector, we pick up the signal, the return signal from the irradiation. This is kind of a cursory description, right? It doesn't really give you a. We're not trying to turn you into a physicist or a chemist, so we'll probably just go with it. Protons are not the only nuclei that could be studied. You can do this with protons or neutrons, and if one of them is odd, if you have odd number of protons and even number of neutrons, you can still do it. You just need the odd number. So that begs the question: with a deuterium nucleus, you have one proton and one neutron. Right? So you got odd numbers of both. You should be able to pick up a signal with the deuterium. But with our deuterium trichloride here, you adjust the frequency so that you're not exciting this particular nucleus. So it's a tuning of your instrument that allows you to ignore that solvent. Right. These are called NMR active nuclei. Right there. Hydrogen, remember, 4 positions around, but have charge here, which in this case is 0. We have the Z, or the atomic number, which is equal to 1. And then we have the A, which is the mass number, which is equal to 1 for a proton. So that's why you have the 1 there, 1H. Just one proton, that makes it. Deuterium should also be active, like I mentioned. Carbon, though, carbon has 6 protons. Carbon has 6 protons and 6 neutrons. So the most abundant isotope of carbon is not NMR active. That's why we have to look to carbon-13. It will have 7 neutrons, still have 6 protons. So carbon-13 is active, but it's only about 1%, right, of the available. So it's more difficult to use that one because it's not as abundant. All right. There are many other options. You can do it for nitrogens, oxygen, fluorine, phosphorus have been used. And usually the instruments, although extremely expensive, are tunable for the different nuclei. So you don't have to buy a separate instrument for each one. Okay, this concept of shielding. Is the origin of shifts. Right? The chemical shift is largely due to shielding. Now, there are other factors, but this is the primary one. This is how we can tell the difference between hydrogens, say, in a compound that is like that methyl group. And then this one has, say, an oxygen and a hydrogen. And this one, let's just say it's carbonyl. And so the acetic acid, right? That hydrogen is going to give you a different chemical shift than these hydrogens do because of its neighborhood. And it's largely due, not entirely due, but largely due to this concept of shielding. All right, so let me get my comments here going. So all these protons don't absorb at the same frequency. If they did, then every spectrum would consist of just one signal. we'd been unable to use NMR if that were the case. Protons in the same molecule can absorb at different frequencies because of the electron cloud that surrounds each nucleus. Now that begs the question. They must be, you've got a strong magnetic field, and then you're scanning radio frequencies. That's the only thing that makes sense based upon, and I'm using the author's words here. You have to be scanning frequencies to determine which ones are absorbing. Okay, so what's the effective magnetic field? The effective magnetic field will determine what frequencies are absorbed by each proton. So you have the external field, and then you have a local field that's generated by the proton itself, by the nucleus, right? And it doesn't always, but in this example, it runs in opposition to the external field. So it decreases the effective magnetic field. That's why they say plus B local magnetic field equals B, what do they call it? Effective field. If this is negative, in other words, if the magnetic field is opposite to this one, then it's going to reduce this value. And that's called deshielding. Shielding. That's called shielding. All right. So we get an induced EMF or electromotive force, reducing the effective magnetic field. So when that happens, this local magnetic field, the effective magnetic field, excuse me, causes the protons to be shielded. So each distinct type of hydrogen atom in a molecule gives rise to an individual signal in the proton NMR because of that shielding effect. The extent of the shielding for a particular nucleus depends on the surrounding electrons and atoms within the molecule. So that gives us information concerning the environment of each one of the atoms, protons. We're focusing on protons now. So protons that are in identical chemical environments, like these are all identical chemical environments, will give you the same signal. But the peak will be taller because there are three of them. Okay, this is called homotopic, chemically equivalent. If protons are in different environments, then you have a heterotopic, and that gives you a different chemical shift. So this will be a unique proton. These will be identical in the NMR spectrum. All right. So here's an example. Let's see, what do we got here? Ooh. This is propanoic acid. All right. So there we've got chemical shift on the x-axis, and the amplitude doesn't have a label. So if we look at the spectrum, we see three peaks, right? The peak on the far right is set arbitrarily at 0. This is, I forget the name of it. Hold on a second. TMS is tetramethylsilane. Right, so that's like silicon's in the same family as carbon, so it can have 4 bonded things to it. In this case, we've got 4 methyl groups bonded to it. So all of these hydrogens are exactly the same chemical environment. And we set this one at 0 simply because it has the smallest chemical shift of all chemicals we've encountered. So we use it. We usually dope the sample with some of this so we have our 0 point fixed. And we can calibrate our spectrum based upon that 0. Okay, then the other two are assigned to, one is assigned to the hydrogen attached to the alkyne, and the other one is assigned to the one attached to the oxygen. Notice that the oxygen, the one attached to the oxygen, has a greater chemical shift, whereas the one that's in the neighborhood of all those pi electrons in the has the least chemical shift. It's the most shielded. We call the one that the further left you go, you used to call that deshielding. So we find 1 at 3.9, and the units here, parts per million, we'll have to explain that later in section 17.7. But the unit of measure here is parts per million in terms of the chemical shift, that delta value. So we got 1 at 3.9 and 1 at 11.2. All right. So here we now have another possibility. 3-bromo-prop-1-ine. So the proton A, so how many unique protons do you have? Well, you can look at the spectrum and see that you have 2 signals there, 2 separate signals. But you can also, if you have the molecule to look at, you can look at which ones are in different environments. And the A is in the alkyne environment, and the B is in the bromine environment. Right, so the one in the bromine environment has a greater chemical shift. It's more deshielded versus the one that's in the alkyne environment. So the B's are homotopic. Is that the word? Homotopic. Yeah, homotopic. And the A relative to B is heterotopic. Okay. So can we tell, just based upon these 2 spectra, which one belongs to that molecule? Well, we see we've got a hydrogen in one environment with the oxygen on the right, and the other one in another environment with the chlorines on the left. We should have 2 peaks. Right? The one on the right only has 1 unique peak, except for the tetramethyl silane. So the one on the left should be the spectrum for that. It has 2 unique peaks. And that's what the author is going through here step by step. Right, does he say that? Yeah, spectrum 1 is the one that agrees with the formula. Now, if we have symmetry to the molecule, so a plane of symmetry, then the hydrogens that are the same distance from that plane and in similar environments are going to produce similar shifts, chemical shifts. So we say, if we look at that molecule split in the middle, it's 1, 2, 3, 4, 5, 6, 7. So it's heptane. This normal heptane has a methyl group on one end, a methyl group on the other. If you flip it over, it looks the same. So those 2 on the end are similar hydrogens. So the 1 and the 7, the 1 and the 7 are the same hydrogens, NMR speaking. And then the 2 and the 6 are same. Right? And then the 3 and the 5 are the same. 5. And then the 1 in the middle, the 4, is by itself. So we should have 1, 2, 3, 4 hydrogens that are unique, will give unique signals. Yeah. So there we go, there we go, there we go. And 4 sets of protons are distinct from each other. it didn't show us an NMR spectrum for that, so we'll have to move on. So this is, I get the feeling this is not like jumping into the deep end of the pool. This is more like jumping into a quicksand. You sink slowly. Okay, for each hydrogen atom in question, here's your strategies for determining distinction. Now, sometimes it's really easy. Like the ones that we've looked at, the molecules we've looked at so far, it was easy to tell the difference. Sometimes it's a little more difficult. So this is a technique that helps you, that is more broadly applicable. So you have your molecule, and you just take one of the hydrogens and substitute an X for it. And you do that for each one of the hydrogens. If the X substituted molecules are either identical or enantiomers, then the corresponding hydrogen atoms are chemically equivalent. So if you put an X in this side, and then you get over here to this side and you're comparing them, then if you can see that these two are enantiomers, then those hydrogens are equivalent. If they're diastereomers, then they're not equivalent. They're distinct. Or if they're constitutional isomers. If they're structural isomers, then you know they are also different. All right. So here's the question.
No.
Oh, okay. 2,2-dichloroethanol. And we have labeled each of the hydrogens, A, B, C, D, and we're not saying that they're different yet. We're just saying they're unique hydrogens. They're separate hydrogens on the molecule. A, B, C, and D. We want to see if any of them are the same. So if we compare X on the A versus X on the B, those are constitutional isomers. If we treat X as, say, a different atom, so it's an imaginary atom. Right? If we put an X there instead of a hydrogen, does that create an isomer? Right? If it does, and it's an enantiomer, then we know that they're equivalent hydrogens. But if it creates a molecule that is a constitutional or diastereomer, then we know that those two hydrogens are distinct. So if we compare substituting for A or substituting for B, those are constitutional isomers. Right? There's this different connectivity. So the A and B are unique. B and C, however, are enantiomers. Notice that for A, the X was attached to an oxygen, and then B was attached to a carbon, so definitely those are constitutional isomers. But if we go from B to C, we've replaced an X on a wedge versus an X on a dash. Then we compare those, and those are enantiomers. So those B and C are equivalent. Right. So now we have we have two unique hydrogen types, and then we compare C to D. Those are also constitutional isomers to each other. So we have actually three unique hydrogens out of this procedure. Okay, I need to be using my animations. I went to all that trouble to create them. I might as well use them. Okay, so what do we have here? This molecule is chloroethene. Chloroethene. Use this technique to determine how many chemically distinct hydrogens we have. So if we put an X, so there's the molecule with no substitutions. Then if we put an X on this one, and we put an X on the B and X on the C, how do they compare to one another? A and B are diastereomers. So those are unique. C is a constitutional isomer of A and B. So C is also unique. So we have 3 distinct protons in this molecule. We should get 3 signals. All right. Now, if we look at this chair flip for cyclohexane, we see that the hydrogen that's pointing up now is axial, then it becomes equatorial in the chair flip. That's a different environment. It's a different magnetic environment with your neighbors. So we should get a separate signal for that one. Here's the problem. We only get one signal. And here's the explanation. These chair flips happen so fast, 10 to the minus 5 seconds for a chair flip. And since the NMR takes a second or more to make a measurement, then it's not going to see the difference. It can't resolve the difference between those two. So NMR is not going to see the difference in hydrogens for this chair flip. Now, that's that happens 10 to the minus 5 seconds for each chair flip happens at room temperature. So that's a relatively high temperature. If you bring the temperature way, way, way down, cyclohexane is, let's see, cyclohexane. It's a liquid at room temperature, boiling point about 80 degrees. So I'm not sure what the freezing point is, but if you brought it down to where you could make a solid out of it, then possibly you could resolve the chair flips and get 2 signals. But you have to get it really cold to slow down those chair flips. Okay. Similarly, this time scale problem with NMR is also seen in rotations. So if we look at the Newman projection, where we had the circle and then the 3 prongs, and the bond, you're looking down the axis of the bond and it's rotating, those hydrogens are moving in and out of different chemical environments, right? So you should be able to see a difference there, except that it happens really fast too. So we can't detect the rotational differences either. Now, of course, if you have a double bond there between those 2 carbons, right, they're locked in place. Now you can see them. So this is only going to have, actually this molecule will have 2 peaks. One at the very small chemical shift because of lots of shielding, and then one that's deshielded attached to the oxygen is way out here at almost 12. Now, there are a couple of effects that will modify the chemical shift values that you get, right? And this chart, and I think I gave you a copy of this, didn't I?
Yeah.
This chart, actually, there's more to this chart. It's on the second, I think the second one. Yeah, it goes up to 20. So we're starting at 1. We're going to start at 1 because that's our 0 point, tetramethylsilane. All those hydrogens are equivalent and they're taken as 0 chemical shift. Then if we have an alkane methyl, a terminal methyl group, we should get a chemical shift of about 0.9. So that's not very much. If we have another R group, another carbon, say it's a secondary hydrogen, we get a shift to 1.3. So we're starting to deshield it. If we have a tertiary carbon, we get a 1.4. So there's not much of a change there. Then 5 actually will be on the next page. 5, if we go to this is called a vinyl hydrogen. Right, you've got a double bond and then a carbon, a methyl group, and the hydrogen on that methyl group is in the vinyl position. Those vinyls are 1.7. All right, so we're starting to de-shield more and more. And we can just keep going on up. So you got values for each one of those. Okay. So the chemical shift is generally governed by the identity of the surrounding atoms and the type of bond in the range of 0 to 12 ppm. This is for protons, 0 to 12. When we get to other atoms, like when we use carbon, it's going to be several hundred ppm shift. All right, so I'm going to skip over that. So this characteristic chemical shift is due to the effective magnetic field surrounding the proton. And it depends on the extent to which the shield the proton is shielded by surrounding electrons. So if we can decrease that effective magnetic field, then we can start to de-shield it. Hold on a second. Let's go back to the formula. The external plus the what was it called? Local. Local equals the effective. Okay. So if we have, if this one is large in the opposite direction, we have a small effective magnetic field around that proton. That gives us a small shift. If, on the other hand, we increase this negative value, then we start to decrease the effective magnetic field. So that's why that statement, if the extent of the shielding the proton is decreased, make this more and more negative, then the proton is de-shielded, then the effective value increases. Excuse me. No, that would have to be, this would have to be increased. This would, if this is negative to begin with, then it would have to be less negative. If we can make it less negative, we can decrease the effect of this local field, then we can increase the effective. And that will cause the shift to be greater. There's a problem with terminology there. And we're going to get to another term here in a minute. That is, you just have to learn what it means. So an increase in the effective magnetic field causes an increase in the energy separation between the alpha and the beta. So this starts to increase separation of the alpha and the beta, which means you get a larger chemical shift on the graph. Okay, so putting these ideas together, the chemical shift of a proton will increase as the extent of de-shielding increases. The more de-shielded a proton, the more positive the chemical shift farther to the left. This is called a downfield shift. And this is sort of grandfathered in from the development of NMR. They called it downfield shift. So just say, if it's a downfield shift, then the chemical shift is getting greater, larger. To the left is a downfield shift, and to the right would be an upfield shift. So two major factors influence. We've looked at the sort of the baseline of, so a methyl group is 0.9. That's just a primary methyl group is 0.9. The nice thing about it is, in the absence of these other effects, those values appear in the spectrum at the same place for each one. Then we have to modify it with these conditions: inductive effects and magnetic anisotropy. So we're going to look at inductive effects first. If I can get that thing out of my way. No, backwards. No, stubborn. Okay. So if we look at a proton that's a primary methyl proton on the left, its chemical shift should be 0.9. But if also attached to the carbon is not just the hydrogen, we substitute a very electronegative atom in there. We get an electron withdrawing effect. And when you get a strong electronegative atom attached, fluorine, chlorine, bromine, nitrogen, oxygen, right, they will draw electron density away. And we've talked about this in general chemistry. That's what gives rise to hydrogen bonding. It also causes a downfield shift because you're de-shielding that hydrogen by drawing electrons away from it. Yeah, withdrawing electron density, because the electrons are still there. We didn't do away with electrons just so we could conduct NMR. So in this case, the proton is de-shielded. A higher signal frequency, a larger chemical shift will be observed in the spectrum. So that's a simple concept, this inductive effect. And the inductive effect usually happens within 3 bonds of the hydrogen. So, excuse me, if you have hydrogens here like this, like this, like this, and then you have a fluorine here, that's within 2 bonds. The effect, the de-shielding effect is very strong. But we could also do this. We could say that, and a fluorine over here, and then whatever else. This would still have a de-shielding effect, but it wouldn't be as strong. It's further removed, but it's within 3 bonds of the hydrogen. 1, 2, 3, 1, 2, 3, 1, 2, 3. These are all equivalent, so they'd all be affected the same way. Now, magnetic anisotropy. Let's look at the word. I like to break the words down. Anisotropy is, let's see. So, anisotropy is a word that's composed of 2 Greek subunits. Anisos, which means unequal, and tropos, which means way. So they're unequal ways. They're directionally dependent. This is a characteristic that's directionally dependent. Okay, for this example, we have benzene, right? And we've seen from general chemistry that benzene has these donuts on top, where you have the electrons are distributed evenly around the molecule. The pi electrons are distributed. Okay, that accounts for the strength and the stability of the benzene ring, the aromatics. But for our purposes, once you put them in a magnetic field, you're going to see circulation of electrons, and they produce a magnetic field, right? So magnetic fields always occur opposite to the movement of a charge. So if the charge moves this way, the magnetic field is going to be perpendicular. So when these electrons are moving this way, the magnetic field circulates this way. Well, actually it goes this way. And those hydrogen atoms out there are subjected to that magnetic field, right? That magnetic field then is non-uniform, of course, right? It decreases the further away from the molecule you get, but those hydrogen atoms are there in the middle of that field at a certain distance. And this is responsible for the large chemical shifts in aromatic compounds. It also occurs in alkenes, but we're going to show you a different diagram for that. Okay, so the protons in benzene have a chemical shift of 7.3. Right? You went from 0.9 to 7.3. That's huge. They're de-shielded that much. Well, if we were to look at hex-3-ene, then we find that we have a chemical shift for the protons that are attached to the alkene part of the molecule have a fairly large shift also. So, and inductive effects have no place in this description because we don't have any electronegative atoms attached to them. Now, you could, I assume you can get combinations, right? If you attach electronegative atom onto a benzene ring, this, say chlorobenzene, and it will have an effect on these hydrogens, right? Not just the anisotropy, but the inductive effect should also give them, in which case the distance from this determines how much effect that has. So these would be the most effective, these would be the less effective, and these would be the least effective. So you might even have 3 distinct hydrogen peaks, proton peaks. All right. So we're producing a de-shielding effect, which increases the chemical shift. Right? For alkenes, we have these pi electrons that are sitting out there above and below. Their orbitals are sitting above and below the axis of the bond, and their circulation is this way. So if it's circulating this way, the magnetic field is going this way. Right? So those hydrogens attached to those carbons are in that magnetic field, and that causes a de-shielding also. It's not as strong as the aromatics, but it does cause de-shielding. Okay. So let's see. Magnetic anisotropy de-shields nuclei of hydrogen atoms that are attached on the outside of an aromatic ring to an atom of a double bond, such as carbon-carbon bond, or of an alkene, or of an carbonyl bond of an aldehyde. Right. So if you have an aldehyde like this, you got that hydrogen. This double bond here partially de-shields that hydrogen, but it also has an inductive effect. Like that. And you should even get more de-shielding carboxylic acid. So I don't know. Did we have that in the in that table? Let's go back. Go back to our table. Here we go. Let's see. Okay. There's a number 16 on 17.1 is an aldehyde. So we get a between 9 and 10 shift. Okay, that's pretty substantial. And that's due to, I think, a combination of both inductive and anisotropy. Then we have, let's see. Yeah. Okay. That makes perfect sense. Then how about carboxylic acid? Let's see, carboxylic acid. Here it is. 10 to 12 is even bigger. It's 10 to 12 versus what, 9 to 10? Right. Now we're starting to get that hydrogen is a little too far away to experience the anisotropy. So I think it's largely the hydrogen here would be an inductive effect. You get withdrawing effect from here, withdrawing effect from here. Okay, what slide are we on?
I think we're on 33. Well, I think we just moved to.
Yeah, let me move back over here. Okay, now we're going to talk about alkynes. Alkynes do not deshield by anisotropy. And the reason for that is the direction of the magnetic field. Since we have in an alkene, you've got pi electrons like this. So they can circulate and produce a magnetic field like that. But in alkyne, you have them circulating this way, and then you got them circulating this way. So their induced magnetic field cancels one another out. They're at right angles to each other. So their chemical shift is rather low, 2.4. There's some deshielding, but not much. So strategies for success, predicting the approximate chemical shift values. All right, if we start with a primary methyl group and the chemical shift is 0.9, then if we add an electronegative atom like chlorine, we're going to shift it by what? 4? Yeah, about 4 parts per million. If we put 2 on there, we're going to shift it by another 2. All right, there should be a rule of thumb here coming pretty close. Right. If we have situations that are not covered in the table, then we need a way to estimate them. The first trend that helps us is that the effects are additive. In other words, if you see a methyl hydrogen, then you can start at 0.9, and if you add something to it, you can take advantage of the inductive effect or the anisotropy effect. And there's just additive. So here we have ethyl benzene. So we have 3 distinct, actually, there should be more than 3 distinct hydrogens. We're focusing on just 3 of them. Those 3 hydrogens, the furthest one from the benzene ring will have the least shift, 1.2. Then we get closer to the benzene ring, we get some deshielding. We get on the benzene ring, we get massive deshielding. So we go from 1.2 to 2.6 to 7.2. Deshielding falls off rapidly with distance. Okay, that's one rule. How about excuse me, I got my thing in the way. Chloromethylbenzene. Okay, so if we start with that carbon in the middle at well, the hydrogen attached to that carbon in the on the outside, if we start at 0.9, then we're going to get an effect from the anisotropic effect, which would be adding 1.4 parts per million, and then we get an inductive effect from the chlorine adding 2.2. So we should expect to see 4.5 for that hydrogen attached to the carbon, to the methyl carbon. Okay, yes. So the what is the anisotropic effect on benzene? Do you remember what that value was?
Mm-mm.
Okay. I think it's gonna give it to us, I believe. It- okay, hold on a second. So what I'm getting from this is for every carbon you move away, you reduce the effect by 20%. So let's see, what's the anisotropic effect for benzene? Here we go. 7.3. That's not 20%. Okay. That's a little hard to follow. Here we go. Well, let me read down through it. What numeric values will be assigned to the various substituents? Derive the effect a substituent has on the chemical shift of the proton by subtracting 0.9 from the chemical shift, the methyl. The difference in the two chemical shifts is due to an additional deshielded. Okay. We need to know the substituent effects from table 17.2 are reduced to approximately 20% of the listed value when one additional bond separates the substituent from the, okay. Without the attached phenyl group and the chlorine substituents, that is with no deshielding, the proton shift should be 0.9. All right, that's our starting point. All right. Oh, we're looking at the next slide. The aromatic substituent should increase the chemical shift by 1.4.
If you go to the next slide, it tells you in the benzyl group, it's 1.4.
Oh, the benzyl group. Okay, 1.4. Okay. All right. And then we also have to introduce the increase by another 2.2 for the chlorine. So the chlorine here gives us 2.2. Okay. Okay. So when you add them all up, you get 2.6, which you expect on that. And what I'm looking for is, does it agree with the measured amount? Oh, this is a different molecule.
Oh,
Sorry.
is it?
Yeah.
Oh.
On this page, it's a different molecule. Okay. All right. It generally agrees with the chemical shift that's observed. Okay. I'm not sure how deep I want to go into this. Let's see what we can gain from it. Section 17.2 described how alpha and beta spin states of a proton develop different energies when placed in an external magnetic field. Okay, we got that. Then equation 17.2 right there to the left shows how that energy difference for a bare proton, that one that has no shielding, depends on the external effect. So this is a totally unshielded proton could be calculated. The energy difference between the alpha and the beta state can be calculated from that formula. We need to know the external field. We need to know, and this is measured in Tesla. And we need to have Planck's constant, right? We've used that one before. we need to have this value, this Greek gamma, which is the gyromagnetic ratio, a measure of how sensitive the nuclear spin state energies are to an applied magnetic field. So that will vary. Each nucleus has a spin has a characteristic value. For a proton, its value is that, whatever that is. I forgot to raise that 8 to a superscript. So that 108 should be 10 to the 8th power. Okay, so that gives us a starting point. Then in a typical NMR experiment, values of delta E spin are on the order of 10 to the minus 25 joule, which is about 0.01% of the thermal energy available at room temperature. So thermal energy is going to swamp that difference. So nuclei in the lower energy alpha spin state are in small excess, but that excess is significant. What that means is the alpha's down here and the beta spin state is up here. And at room temperature, you've got enough energy to push these up here. But you have enough left down here, small number down here, so that you still get, you still have the ability to see an activity in your NMR spectrum. So if we recall, the relationship between the energy of a photon is equal to Planck's constant times its frequency, and we substitute that relationship into the equation 17.2, then we get the 17.3 equation, and we can calculate the frequency of the photon that will be absorbed, that we should use, the radio frequency that we should use to obtain a spectrum. We also see that the frequency of the absorbed photon is proportional to the external field. So you increase the external field, make it bigger and bigger and bigger, the frequency is going to go up. All right, this calculation, I don't think I have you doing any of those in homework. Okay.
I haven't, honestly, I haven't even looked at it yet.
Okay.
Well, I looked at it like the first question, but
So the frequency is 3 times 10 to the 8th reciprocal seconds, or 3 times 10 to the 8th hertz. Which, let's just do a little conventional analysis here. 10 to the 8th hertz. So this can be split into that, right? 10 to 6, 10 to 7. This and this is megahertz. And this is 100 times that. So 300 megahertz is a typical frequency that's used in proton and NMR. Right. So this frequency, operating frequency of the spectrometer, has to be equal to the frequency of the absorbed photon. Right? That's a given. If they're going to resonate, they have to be the same frequency. So therefore, if we substitute that operating frequency into our equation, then we find out how strong the magnetic field has to be. Right? So if the strength of the magnetic field is 7.046 Tesla, then we can calculate from the second equation is equal to the units and equals to 106 hertz. A spectrometer with 7.7 Tesla magnet has an operating frequency of 300. There you go. Called a 300 megahertz instrument. All right, so that's enough. That's enough theory. I hope. The chemical shift is a measure of the extent to which a signal's frequency differs from that of a reference compound. And that reference is our tetramethylsilane in parts per million. And that's defined by this expression: the frequency of the sample minus the frequency of tetramethylsilane divided by the operating frequency of the instrument times 10 to the sixth. That's where the parts per million comes in, 10 to the sixth. It's like multiply by 100, you get parts per 100%. Multiply by a million, you get parts per million. So this proton chemical shift is the same regardless of the NMR instrument used to measure it, as long as it's referenced to that same 0 point. So we plot this chemical shift on the x-axis and the, instead of frequency, which depends on the strength of the magnet. The proton's chemical shift is independent of B external, whereas the frequency is not. The frequency does vary with the operating frequency. So that's why the chemical shift is used instead, because it's independent of that signal frequency. All right. So there it is in bold. That's the takeaway from the whole slide. A proton's chemical shift is the same regardless of the NMR instrument used to measure it. Deuterated solvents. Right, we mentioned one a little earlier. Right, most of the solution is solvent, since we have such a small amount of sample in there. Then that means that we've got to do something so that the signal from the solvent doesn't swamp the signal from the sample. So if the solvent contains any protons, then we could get a signal that's dominated by the solvent and not even see the sample. So to avoid this, we use deuterium in the solvent, right? CDH3. And the way to avoid detecting that one is that we use a different frequency so that the deuterium is not detected. Sometimes there's a residual solvent peak because some of the solvent may not be deuterated. All right. Now, you haven't taken calculus yet, but integration, calculus is actually two different things. One is tearing things apart, the other is putting them back together. Right? Differentials are tearing things apart. Integration is putting things back together. So if we've got a signal that's like this, if we integrate it, we're looking for the area under that curve. Right? And you can do that mathematically. Or you can do it iteratively. Right? Mechanical or electrical integrators will simply just slice this peak into columns. Right? They're rectangles, and it'll take the height times the base distance and say that rectangle is this volume. It'll just add them all up. That's an integrator will do that. Rather than taking the formula for that curve and then using an integral formula from calculus. It's easier to do it this way. And if you make the span small enough, it comes pretty close. Okay, so why would we want to do that though? Okay. One of the most important features of the NMR is the ability to compute the area under an absorption peak. called the integration of the signal, okay? This is important because the area under the peak is proportional to the number of protons that generate that peak. So it's not just the height of the peak, which will be true, right? The height of the peak will be higher for more, but the linear accumulation of the number of protons is due to the area under the peak, not to the height of the peak. Okay, so most modern instruments will digitally integrate for you. Okay, and sometimes they'll actually superimpose that integration on your screen as this blue line. The difference between this level and this level, and notice as it crosses the curve, it goes like this. It's adding up these rectangles as it goes. It goes here, it goes like that. So the more rectangles it gets, the higher it gets. And then when it gets to the other side, then it's flat again. So the difference between these two is the area under that curve. Okay. And that will give us information as to the number of protons that are represented in the signal. Right. So here we have a trace from 1,4-dimethylbenzene or paraxylene. Excuse me. And we're looking at an integrated signal across those peaks. Right. The most deshielded one is, the most deshielded one is the one that's right close, is on the benzene ring. So this hydrogen here, these hydrogens are equivalent. Then you have a methyl group here and a methyl group here. These hydrogens are also equivalent. So you have two signals, right? One from here and one from these. This is further removed. These hydrogens are further removed from that anisotropy effect. So they're going to have less deshielding. These are going to be the most deshielded. They're going to be the farthest, the highest chemical shift. And then this trace is integrating them. Notice the difference in the heights of those when it went from here to here, and then it went down here, and then it went like that. Right? The difference between these two shows you the ratio of one type of hydrogen to the other one. So the ratio should be 1, 2, 3, 4, 4 here, and 6 here. So the ratio should be 6 to 4, or 3 to 2, or 1.5. And there you go, 1.5 to 1 is the ratio of those hydrogens. That can give you some valuable information when you're trying to construct the molecule. You know how many are actually represented by that chemical shift. Okay, now let's talk about signal splitting. Thought it couldn't get any worse, right? We can have what? At poor resolution, these peaks would look like just a single peak. But at higher resolution, this 1,1,2-trichloroethane shows us two peaks, right? Because we have 1,1,2-trichloroethane. Ethane, right? That's ethane, right? Yeah, ethane. 1,1,2. So we've got, let's see, where do they put it? They put the chlorines here. So this is 1,1 with a hydrogen here, and then 2 with 2 more hydrogens here. These hydrogens are distinct from one another because they're in different chemical environments. This one has 2 chlorines inductively withdrawing electron density away, and this one only has 1. So these hydrogens are different from that hydrogen. And they will show different chemical shifts. These hydrogens, this hydrogen will have a greater chemical shift because there are two chlorines. So it's going to be furthest to the left. What happens, let me see, I've got a description here, text. If we magnify the peaks, we see that they're actually split. Now the split is centered on 5.7 something for this one, and centered on about 3.987, something like that for this one. But then they split from that place up there. I'll tell you about that in just a second. I've got a story. Why does this happen? Every proton behaves like a tiny bar magnet. Okay? That can either be spin A or spin B. So the magnetic field experienced by a proton can be altered by the magnetic field of nearby protons. These are close enough. Right? They're within 3 bonds of each other. So they have an influence on the other one. So the apparent chemical shift can be altered by those other protons. We call that spin-spin coupling. They're said to be coupled to each other. Okay, so this proton will affect these, and these will affect that one. So if this one has, if we have a peak, if this is 0, and we have a peak, say, out here and one out here, then this one is going to be there, and this one's going to be, should be bigger, like that. But if we magnify it, we find out that at this point, this one is split. It has, I look at it as 2 nodes. 2 of these cause 2 nodes in this one. So we have like this, like that, and like that. So there are your 2 nodes right there, just due to these 2. And this one, there's only 1 influencing those, so it only has 1 node. Right here. Okay. Now there's a formula, but I like the idea of thinking in terms of nodes. It's the N+1 rule, and that N is not nitrogen. N is the number of coupled protons. So if this one is coupled to 2, then 2 + 1 is 3, and you'll have a 3-part split. This one is coupled to 1, so it's N+1 is 2, it'll have 2. You can do it either way. All right, we call, if there's no splitting, we got a singlet. This is a doublet. This is a triplet. You can get quartets. You can get quintets. Anything bigger than that is a multiplet. And then the relative peak heights, we're going to talk about that in just a second. We're going to use a thing called Pascal's triangle. You ever heard of that? Okay, it's a mathematical thing that Blaise Pascal came up with back in the right around the turn of the 19th century. Okay. Oh, all right. So here we have, we're back to these. Why are we back to this one? We're back to 1,4-dimethylbenzene. 1,4-dimethylbenzene. Okay, so that's para-xylene. Methyl and aromatic protons are not close enough to be coupled. Oh, I see. These protons are too far away from each other. The equivalent protons are not going to cause splitting, of course, but they can't be coupled to the methyl protons because they're too far away, right? If you have this like that, and you have, let's see, yeah, there's a hydrogen here, and then you got a carbon here, and it goes out here to a methyl. These hydrogens are 1, 2, 3, 4 bonds away. That's too far. They won't couple. got to be 3 or less. Okay. So this describes the origin of the doublet. There are two possible values of local. Okay. The origin of the n plus rule can be understood by considering various magnetic fields. The local field generated by the protons themselves, responsible for splitting a particular signal. The proton that generates the signal, shown in black, there it is, yeah, the hydrogen on the left, generates the signal that's going to be split. The proton that generates the signal shown in black is coupled to one proton on the right. Therefore, there are two possible values for the local magnetic field from that coupled proton. You can have both of them going in the same direction, or you can have them going in opposite directions. So when they're coupled like that, if they're both going in the same direction, you get one peak. If they're going in opposite directions, you get a separate peak. That changes the energy, the frequency, the shift for each one. So that's why you get one proton splits into two signals, a doublet. What if you have two? Right, so that black one again produces a signal, and then what are the combinations that you can have? Right, you can have two. Well, actually, let me go back. That's not the proper interpretation, right? The coupling proton is the one that is either spin up or spin down, alpha or beta. So that gives you two possibilities for influencing the local magnetic field around the coupled hydrogen, the signal hydrogen. Okay, right. Now, if you have two of them, you can either have both up, or you can have an up down, or you can have both down. So you have three possibilities there for altering the magnetic field, the local magnetic field. That's why you get three peaks there. What if you have with two coupled protons, right? You have those possibilities and you get a triplet. If you have the case of three equivalent hydrogens, then you can have three up, you can have two up, one down, or you can have two up, one down, or two up, one down in that combination. Or you can have one up and two down, or you can have three down. So you have four possibilities there. Well, since the two middle ones have three possibilities to give you the same magnetic effect, then those two split peaks in the middle are going to have three times the height of the ones on the end, because they're only due to one possible spin combination. All right. And you get a quartet out of that one. Okay, here's Pascal's triangle. In order to construct Pascal's triangle, you start off with one at the top, and then you have this. From here on, now you add two to the two neighbors to get to the middle one. So this is still going to be one here. Add these two together, and then one here. So that's the first part of the triangle. Then you have one here, add these two together, three, two together, three, there's one there. Then add these together, you get 4, 6, 4, 1. And it just keeps growing as far as you want it to go. So when you look at the relative peak heights, you see them spread. If it's a triplet, you're going to have the middle peak is twice as high as either peak on the side. If you have a quartet, these two middle peaks are going to be 3 times the height of the one on the outboard ones. If you had a quintet, it would be 1:4:6:4:1 ratio in height. So Pascal's triangle gives us a mathematical expression for relative peak heights. Now, that's when you have a pure split. We're going to get into some combination splits here in a minute that kind of muddy the water. Okay, so in this case, OH and NH protons often do not exhibit coupling. Right, in this one we have NH. Okay, this molecule has an amine group on the end, terminal amine, and its hydrogens give us almost nothing. Right, there's a reason for that. They often produce this broad singlet. They don't appear to couple to any other protons. And they appear not to affect very much. There's a little bit of an effect, but they don't affect very much their neighboring protons. The reason for this is a time effect. There's a proton exchange that tends to this rapid proton exchange happens faster than we can do a scan. So we can't see any difference in it. It tends to muddy the waters. Hydrogen bonding, and then which weakens bonds, will allow proton transfer among molecules. And that's why you get this broad peak rather than a sharp peak, because you're averaging in all these possible positions for the hydrogen as it's transferred. And it just sort of flattens things out. So they can hop rapidly from one nitrogen or oxygen atom to another. It's usually faster than the NMR can acquire the spectrum. Now, again, we could probably cool it way down. Maybe you could get it cold enough to where you could actually see the effect. But we have to, the signal that we get is an average of the environment that they're in. And because they're moving from one place to another, they're passing through different chemical environments, and you get a mishmash, a large range of frequencies that give you this kind of just a hump rather than a peak. Okay. If a sample treated with, I don't know what you call that, dideuterium oxide, it's deuterated water. The OH and NH protons on that sample are rapidly replaced by D, whose signal do not appear in the NMR spectra. So the intensities of the OH and the NH signals decrease dramatically or disappear entirely if you introduce deuterated water into the environment. That's one way to test what you're getting, right? Is that really one of these? Well, you can, let's put it this way. You know what the molecular formula is. Does it have oxygen in it? Does it have nitrogen in it? Right? If it's got either one of those in it, and you hit it with deuterated water, then you're going to see the signal decrease. That small hump will just disappear. So each peak in a split signal represents a slightly different frequency being detected. And there's a difference between those two peaks called the coupling constant. It's in units of hertz. That is the difference in frequency between those peaks. And these are characteristic of different kinds of protons. Right? So if you have 2 methyl protons, coupling constant is going to be between 6 and 9 hertz. If they're too far away from each other, of course, it's going to be 0. And if they're coupled through an alkene, then you get a different value, a slightly higher value, coupling constant. So the split, instead of, if it's just a doublet from an alkane, it's going to be like that. And a doublet from an alkene is going to be a little wider. And your instrument can spit those numbers out. Right? It can measure those things for you so that you don't have to go in there with a ruler and try to figure it out. All right. So coupling constants can be used to interpret NMR spectra. The signals of the protons are coupled together, exhibit the same coupling constant. In other words, if in our example there, let's see, we want unique. So A and B are unique because A is on the side with the bromine, B is on the side with the ethyl group. So A and B are different. They are close enough to be coupled together, right? At the top of that molecule. A and B hydrogens are coupled. So they produce a doublet in each other. The coupling constant in those two doublets are exactly the same. So when you couple this hydrogen with that hydrogen, any split, the coupling constant is going to be the same for both of them. And if we couple the C and D, right, we're going to get a coupling constant of 7.6 for either one. One of them is a triplet, one of them is a quartet, but the coupling constant is exactly the same. That can also help you decide in a complex spectrum, that can show you which ones are close to each other. Right? You can tell from the split that D is split by 2 hydrogens in its neighbor. And C is split by 3 hydrogens in its neighbor. So that can give you information as to how this thing is connected. Okay, here's some complex signals. All right, why do we get these complex signals? Okay. When the protons that produce a particular signal are coupled to 2 or more distinct types of protons, right? If there's multiple coupling, then you can get a complex signal. So let's say B in this case is coupled to A, but it's also coupled to C. So you can get a complex split for the A signal. Right? And here we see this A resolved on the right. One of these couples is due to the A, and one of them is coupled is due to the C. And then B, of course, excuse me. Well, hey, let me see. Yeah. 1, 2, 3. Okay, so A is 3 bonds away from C, and B is 3 bonds away from A and C, and A is 2 bonds away from B. So all 3 of those are coupled, and they show a complex pattern because of that fact. Now, if the separations are sufficient, then you'll have different coupling constants for the complex splitting. And it doesn't show us the values here for the coupling constants. I wish it did. Okay. Oh, there they are, coupling constants. So HA is coupled to B by a coupling constant of 1.8. So A is coupled to B by 1.8. So one of these is coupled to B, has 1.8. B is coupled to C by a coupling constant of 7.1. So we can tell them apart. Okay. And that's probably what you're going to see most of the time. complex, unless your molecule is really simple. If you're investigating complex molecules and you try NMR, you're going to get a really, you're going to have a bear by the tail. Okay. So if we look at each one of these separately, then we get some idea as to how the splitting occurs. Right. If we look at, say, B, and B first is split by C. B occurs at 5.97, and the first splitting of B is by C, then the coupling constant is 7.1. So we notice that the first split is between these two majors right here. Then we introduce a split with C. So C then is going to split with 1.8. Let's see. Consider the coupling between, oh wait, excuse me. No, B split by C gives you the bigger coupling constant. And then we're going to split those split signals by A. So first we split B by C, and then we split B by A. And the A split is 1.8 hertz. If we look at it, when you can look at it two different ways. If we split B by A first, and then split each one of those by C, then we get the same spread. So it doesn't matter where you start. It's generally easier to construct these splitting diagrams by working order from the largest coupling constant to the smallest one. Okay, so these two protons on carbon 3, well, yeah, they split the signal on hydrogens on carbon 2, but we also get a split from the carbonyl, the aldehyde hydrogen. So we get a doublet split from the carbonyl hydrogen, and we get a triplet split from the secondary carbon hydrogens. All right. So we get a big triplet split, and then each one of those is a doublet split, a triplet of doublets. And this was butanal. Okay, triplet of doublets. 1, 1, 2, 2, 1, 1. Okay. As far as peak heights go. So I'll look at it this way. It's a 1, 1, 2, 2, 1, 1. So that fits with Pascal's triangle. Hexane 3-one. All right, we've got some really complex things going on here. Hexane 3-one is taken with a 90 megahertz spectrometer and a 300 megahertz spectrometer. So we can, very often we can resolve unresolved peaks by using a higher magnetic field, stronger magnetic field, going from 90 to 300. And that's shown on the next slide. The 300 megahertz is on the next slide. This is the 90 megahertz. It should be easy to see that the uniformity of those peaks is not very good. Right? They're not sharp peaks. They're really ragged. That might be an indicator that you've got unresolved splits. Okay. Does not show where the signals overlap. Okay. If we go to a 300 megahertz spectrometer, we can clearly show the two distinct splits. So at position 1, let's go back. On the other one, position of 1, we saw 1, 2, 3, 4, 5 overlapping methyl signals. We know they're methyl signals because they're close to 0.9. And then when we split them, we don't have 5 peaks. We actually have 6. We have a doublet of triplets. So they were so close together, we were getting some overlap, and the middle was overlapping into what looked like a single peak. All right. You get better resolution with a stronger magnet, because the coupling constants are independent of the external field. Therefore, regardless of the strength of the external field, the frequency difference between the peaks of the split signal remain unchanged. Grouping occurs at the same chemical shift for either spectrometer. Okay. You get better resolution as the magnet becomes more powerful. But the coupling constants are independent of the external magnets. So what that's saying is that the position, the chemical shift position in parts per million is going to be exactly the same. It's going to be centered on one. But with a stronger magnet now, we can resolve the peaks. So we didn't actually change the position of all those peaks. We just resolved them. So this increasing the external field causes an increase in the delta E spin, which changes the signal frequency. And that resolves the peaks. It goes back to that equation that we had earlier. Oh, we got more explanation here. Okay. In the top figure A, we see two unresolved signals are plotted with frequency on the axis. Okay. As the strength of the magnet increases, the centers of the two signals move apart. Okay. But the frequency separation between the peaks remains essentially the same. Okay. So the overlap occurs in the middle. And that's what you want to do. You want to move those splits apart so that you can resolve the one that's overlapping. Okay. When we do this, the signal width in units of parts per million becomes narrower with a stronger magnet. Okay. All right, now let's look at carbon. Because sometimes you can get some useful information from doing NMR of carbon. But like I mentioned earlier, the problem with using carbon is that we have to use carbon-13. Can't use carbon-12 because that's an even number of nucleons. So they're similar, both the proton and the carbon-13 spectrums are similar with respect to how we present them, with the axis labels and units. But the frequency of the radiation that is used to radiate a sample is significantly lower than it is for hydrogens. And that has to do with that equation where the gyromagnetic constant is different. It's about 1/4 that of a proton. So we need to use we need to use a lower frequency, not as much energy is required. And when we do that, that also ensures that we don't get proton signals mixed in with our carbon signals. Because if we use a lower frequency, then the protons are not going to respond. Right, here's the challenge. The carbon-13 isotope is only 1.1% of carbons. So the problem is your chances of getting a signal return are much lower. And they're not going to be as strong because there are not that many of them in there. Right. So that gives rise to signals that are often buried in the noise. That's what that the A graph at the top. See, lots of noise. Right. There's a way around that. And the way around it is averaging. We get this noisy spectrum. Our chloropropane is the example. we get this noisy spectrum. And we look at this in terms of unique carbon atoms also. So each unique, chemically unique carbon atom is going to give us a peak. So we average a large number of spectra, sometimes thousands of them, in order to acquire an output. And that's really, as far as the technician goes, it just takes time. Right. Instruments, modern instruments now, they will do all this. They will measure and remeasure over and over and over again, thousands of times, and average them all together for you. So it's not tedious. It's not tedious work. It just takes time. So we can improve the signal by averaging, signal averaging. All right. We still have our tetramethylsilane as the 0 point, but we also get a solvent peak, because now we have, if we use the deuterated trichloroethane, we're going to get carbons in there. We're going to get carbon 13s in the solvent too. So we have to be aware of that peak. It looks like it occurs somewhere around 77 or 8. All right. We can get the number of chemically distinct carbons. That's good information. In this case, we should get 3 chemically distinct carbon atoms in chloropropane. Right? So we have the chlorine here attached to this carbon, and then 3 carbons. So we have a carbon here, and a carbon here. The distance from that chlorine and the number of hydrogens attached to them determines whether they're unique. And we do have 3 unique carbons. So we should get 3 signals. Notice also the range of the parts per million chemical shift. Right? We're not just looking at 12 and 13 now as maximum. We're looking at 200 or 300 parts per million as a chemical shift maximum. And it's all based upon that, not the first formula, but the second formula. Okay. Let's see. I had a lot of text to put in this, so I had to duplicate the slides. Yeah, okay, there it is. I get pretty close. I say 77 is the solvent peak. So as long as you know where the solvent peak is, and you don't have any carbons that are going to appear near that, then you're okay. As long as you can tease out the unique carbons without interference from the solvent, then you're in good shape. We can compare the locations of the carbon atoms relative to a unique point of reference. Okay, that's what we're doing. We could apply the chemical distinction test, in which we first substitute an imaginary atom for each carbon and then determine isomeric relationships. That's another way to do it. Carbon 13 nuclei have spin, and they undergo coupling with other nearby nuclei that have spin, such as protons or other carbon 13 nuclei. However, under most conditions, the spectra won't show signal splitting. And that's by choice as much as it is by the fact that there are so few of them. You can't split something that's not there, or it's so low, you can only split it with so much intensity. Right? Well, actually, 1 out of every 100 carbon atoms is a carbon 13, so it's difficult to detect them. Natural abundance reduces the splitting. We also have what's called broadband splitting. we essentially turn off the coupling between carbon and hydrogen nuclei, because the hydrogen nuclei are still there and they can influence the environment and cause coupling. But it's also selective by the operator. Right? Broadband decoupling is a procedure that continuously sends a specific range of radio frequency radiation through the sample, forcing all protons to flip back and forth rapidly between alpha and beta spin. So that removes them from influencing the carbon spectrum. This addition of frequencies increases the signal intensity also, and that helps clean up the spectrum, moves everything out of the background noise. Although there's a disadvantage, of course. There's advantages and disadvantages. We lose valuable information about the number of protons attached to each carbon based upon this spectrum, but you can get that from proton spectrum. Or you can use DEPT spectroscopy, and that's coming up next. All right, so here we have the different chemical shifts for the unique types of carbons. I said 300. They typically don't go above 220 parts per million. The trends in chemical shifts are about the same for both carbon and proton signals, because shielding and deshielding phenomena affect both. So we get an increase for the carbons in a increase in deshielding or chemical shift for these phenylcarbons. All right. What do we have here? Thought I put the name on that. Right. See. Let's see. Down. Yeah. There. And then we have. So this is an aldehyde. So this would be, what's the longest group? Chain 1, 2, 3, 4. Right. That includes this one. 1, 2, 3, 4. Okay. So this would be a 2 methyl. 2 methyl. 1, 2, 3, 4. Butanone. 2 methyl butanone. Okay. So what do we have going for us? Well, we can identify the zero peak, the tetramethylsilane, and then we can, the deuterated trichloromethane is at this peak. So we have 1, 2, 3, 4, 5 unique carbons. Is that true based upon this? That's a different environment. That's a different environment. 1, 2, 3, 4, 5. Yeah, we have 5 unique carbons that are going to give us signals. Now, the one that gives us the most shift, probably this one closest to that oxygen for why do I keep forgetting that word? Induction. Got it. The inductive effect. Okay. Unfortunately, the area under a carbon peak is not very well correlated with the number of carbons due to broadband decoupling. So if we see these peaks down here are the tallest, we would think that they might be due to this, maybe this carbon or that carbon decoupling. They might be influenced by the number of carbons for sure, but the area might be influenced by the number of carbons, but I wouldn't expect it to be based on this statement and the reasoning. I wouldn't expect it to be related as closely as our hydrogen areas, like our 1.5 to 1 that we calculated earlier. it wouldn't be that reliable. All right. Actually, the area is bigger than expected due to the nuclear Overhauser effect, which don't ask me what that is. Okay. So here we have, let's see. This is DEPT. Let's see. Yeah. DEPT, which stands for distortionless enhancement by polarization transfer. That's a mouthful. So if a specific sequence of RF radiation pulses are applied to this sample during acquisition process, then other types of spectra can be constructed which provide even richer structural information about a molecule. This technique, DEPT, produces spectra in which the signals given off by the carbon nuclei depend on the number of protons attached to each carbon. Ooh, that's good. And it's the information is given to you on the spectrum itself. So the farthest one to the left there, that's a carbon with no hydrogens on it. And the farthest to the right is a carbon with 3 hydrogens on it. Ooh, that's good information. All right. Did I write that ethyl benzene? Oh, that's a different molecule. Okay, here's another technique that can be used with your NMR spectrometers. This is one of the two-dimensional techniques, right? One-dimensional is where you have an X and Y axis. Two-dimensional is where you have chemical shifts on both axes, and then the position in the plane gives you information. In this representation, we're showing coupling. Right? One frequency axis and the second frequency axis corresponds to amplitude. So one frequency axis, let's see, applies all once measured. Second axis corresponds. Oh, this is the normal spectrum. Okay, so for the 2D spectra, you get 2 frequency axes corresponding to, and the third axis is amplitude. Now, the third axis would be into and out of the board, but we're representing it as probably density of the spot. This homonuclear correlation spectroscopy. This is an example of that one, COSY. What do I get out of this one? Well, this one will show you if we label the ethyl ethanoate molecule, label the hydrogens, A, B, and C, unique hydrogens, and then run the spectrum and use the COSY transform on them, then we can say which ones are actually coupled. Right? If we look on the straight line, that horizontal line, then we see there's a spot for B and there's a spot for C on that line. And then if you draw a vertical and a horizontal from each other, where they meet, we find another peak. That cross peak means that those C and B are coupled. They are close to each other. They are within 3 bonds. Yeah. Now, oh, it wouldn't do any good to draw a line across from. Well, we could do either side. Look, if we drew those red lines, well, I don't know if you can see my arrow there. If we drew the lines from this B to that one, and this one down to this one, right? That horizontal and vertical line would show us another one over here. So it looks like they're symmetrical. Right? You get the cross peak here, or you get the cross peak here, showing BC coupling on both sides. And then this, of course, is AA. It can't be coupled with itself. But I assume if you had another A in there somewhere and it was close enough, then it would also show a coupling arrangement. All right. So here we have, let's see, het core spectrum of diethyl phthalate. Okay. Phthalates are dicarboxylic acids of actually dibenzoic acids. So if you have this, and you have a carboxylic acid group here, like that, and you can have one here, you can have one there, you can have one there. So this would be a metaphthalate, this would be a no, orthophthalate, metaphthalate, paraphthalate. If we did this one down here, like that, then that would be phthalic acid, would be paraphthalic acid. But if you form an ester with it, in this case they used an ethyl ester, so we placed it here with an ethyl group, right? So that's diethyl phthalate. And you've seen, I'm sure you've seen advertised, this product is produced without phthalates. They started doing it with baby bottles, get the phthalates out of there because they thought they were injuring the infants when they drank their milk. So they wouldn't produce the plastics that had phthalates in it.
What do they think they are doing with it?
Well, these aromatic compounds can be nasty because they're very stable. I don't know in specifics though. Okay, so this het core is called heteronuclear correlation spectroscopy. Heteronuclear. So that means we're looking at two different nuclei. So the NMR spectrum would have, on the x-axis would be the carbons, and on the y-axis would be the hydrogens, heteronuclear. Homonuclear was the first one, right? Let's go back. Cozy, right? Well, yeah, that's cozy would be, what's the abbreviation? Homonuclear correlation spectroscopy. Where's the H? Should be H cozy, shouldn't it? It's not. I guess because it's homonuclear, we're just going to call it cozy. But if it's heteronuclear, we put the het core in there. So this correlates hydrogens and carbons. I assume you can use other elements too. You can correlate them. Each cross peak provides information about which protons are attached to which carbons. Oh, that's interesting. So we've got the hydrogens on the y-axis, and we've got the carbons on the x-axis, and then we've got the plotting of where they coincide. So the E carbons correlate with the E hydrogens. And we can tell from the hydrogen spectrum how many hydrogens are there because of the way that they're coupled with their neighbors. So eventually you can figure out the connectivity of the carbons and then the connectivity of the hydrogens to those carbons. Right? Sounds to me like we need a computer program that will lessen the torture.
Yeah.
Yeah. That will take these and give us proposed structures. How about that? Okay. These two-dimensional spectroscopy techniques become much more important to structures that are very complex, such as proteins. Oh, and that occurred to me on the way over here this morning. Why did the course content outline include polymers. No, it's obvious because much of biochemistry is polymers, large molecules that are linked together with small subunits. So that's why we're going to look at polymers. So get you ready for biochemistry. Okay. 3 and 4 dimensional experiments can even be carried out. We're not going to go into those. All right. So strategies for success, elucidating molecular structures using NMR. This puts everything together in just a neat package. So information that you obtain from the hydrogen NMRs are the number of signals, right? Tells you how many unique hydrogens there are, or protons. The chemical shift tells you things about their environment, right? And possible electronegative atoms that are nearby. Okay. Integration of the signal tells you how many protons are represented by each one of those peaks. And then splitting patterns tells you their neighborhood, how many hydrogens are attached to their neighbors. And that gives you a lot of information. The carbon-13 NMR spectra, the number of signals that you get gives you the total number of chemically distinct carbons. That's good. And then the chemical shifts tells you whether you have an aromatic ring, double bonds, electronegative atoms also. And then we can combine those into two-dimensional spectroscopy. So stepwise, determine the number of proton signals. Yep. Examine each signal. Analyze the chemical shift. What type of proton is it based upon its position, its chemical shift? Then look at the integrated signals for how many of them there are in those positions. And as we proceed through these various steps, we can say, wait a minute, that step up there doesn't coincide with this step. So I might have to go back up and say, what assumption did I make at this step that isn't compatible with this one? So you might have to go backwards and forwards as you move down. Interpret the splitting, right? Build molecular fragments. Okay, this procedure lets you build parts of the molecule that you're pretty sure this part is true. It's not the whole molecule, but this connectivity and arrangement is accurate. Then once you get your fragments put together, then you put those fragments together to build the whole molecule. It's like fitting a puzzle together. Okay, so here we have an unknown, C10H12O2, and we've got a spectrum with 1, 2, 3, 4, 5 proton signals at 1.1, 1.8, 4.2, 7.4, and 8.1. There are at least 4 distinct types of protons. 1, 2, 3, actually I count 5. 4 distinct types. 1.1, 1.8, yes, 4.2, and a set of signals between 7.4 and 8.1. Those are very complex signals. That's why we're saying at least 4, maybe 5. Yeah, okay, I get it now. So we construct a table for each one of these entries, right? We put the chemical shift values here. We say, what could they be? Nearby double bonds or electronegative atoms, right? For the first one, probably none. Second one, probably none. The third one could be an oxygen, right? Because we do have an oxygen in the molecular formula. And this big shift is pretty close, for number 4 is pretty close to what we would consider for aromatic. And then we look at the relevant integration, which tells us the number of protons that are represented there. Well, 1.5 to 1 to 1 to 2.5, we need whole numbers, right? You can't have half atoms. So we multiply by a factor, and that gives us 3 protons at the first signal 2 at the second signal, 2 at the third signal, and 5 at the fourth signal. 5 at the fourth signal probably means that you do have a benzene ring, more than likely. And then we look at the splitting patterns. Right? So the first one is split into triplets. That means it has it's in the neighborhood of 2 distinct hydrogens. A sextet for the second one means that we probably got 5 hydrogens in its neighborhood. And then a triplet for the second one, and the last one is very complex. So we can't interpret that just yet. And that's what these steps are talking about here. Now, when we get to this part B, where we say molecular formula shows that there are actually 12 hydrogen atoms in the molecule. So, well, I did it for the reason because we can't have half atoms, but they did it for the reason we need 12 atoms in our formula, and 3 plus 4 is 7, 7 and 5 is 12. Okay, so if we have 3, 2, 2, and 5, we have 12 hydrogen atoms. Okay, so that fits. So each relative integration value gives to us must represent 2 hydrogen atoms. So each integrated value that we get is 2 hydrogen atoms. Even the split peaks, right? Each split peak will give us 2 hydrogen atoms. Let's see. So we looked at the splitting. Our neighbors have so many atoms in them. No, so here, I'm not going to go into a lot of detail here, just to say that we're building pieces of the molecule here. So if we go to 1.8, we find that it's 1, 2, 3, 4, 5, 6. We get 6 splits. That means these 2 protons have to be split by 6 neighbors. 5 neighbors, excuse me. If we have 6 peaks, that's 5 neighbors. So we have a terminal methyl group, and a secondary carbon with its hydrogens would give us 5. So that's where we put the 1.8 hydrogens for the carbons. And we go through that procedure. I'm more interested in that mess out there to the far end. That's part of these phenyl protons. All right. By using a simple methodical approach, propyl groups, and okay, maybe it's going to be on the second page. Well, they're not even bothering to analyze that mess out there to the left. They're just saying that's probably the phenyl group. Right. So there we have what? 1, 2, 3 unique protons, it looks like. And then attached to the rest of the molecule. So when we put it all together, the most likely structure is a benzoate. 1, 2, 3, a propyl benzoate. All right. So we've got determine the number of carbon signals and analyze the chemical shift. All right, so the carbons, and we do a similar thing. We can use DEPT to help us use 2-dimensional techniques. We can also use IR spectra to help us also. This particular molecule we know has, it must have a hydroxyl group, right? Because of the position of that really broad band out there by 3300. So we've got to have a hydroxyl in. And we have 1, 2, looks like 3 unique carbons. Come on. Okay. We have 4 different types of signals generated. 1, 2, 3, 4. Yes, we do. 4 different types. We only labeled 3 of them. Oh, that's probably the solvent. Yeah, that one at 77 is a solvent. So I don't know why we said 3 unique ones. We only have 4. We have 3 unique ones. One at 26, 33, one at 73, and 77 is the solvent. Yep. Okay. So only 3 of these are unique. That's what I would have said. All right. So we set up our table and we say, what other chemical shifts? Are there any nearby atoms? The first 2 are fairly consistent with what we know about carbons and their chemical shifts. The last one at 73 is probably influenced by the hydroxyl. So the CH2 from the DEPT spectrum should have a hydroxyl attached to it. And then, was there any splitting on that third one? Splitting on the third one. Can't tell. Can't tell if there's any splitting. Oh, there's no splitting with carbon. Excuse me. Okay, so it's attached to the electronegative atom, the oxygen. Right. Then we generate these possibilities and then we piece them together and we end up with that molecule, which should be 1, 2, 3, 2,2 dimethyl propanol or propane 1-ol. I think they write it that way. Okay, we're done.